So yes, students, this is Divak Shah from Engg Institute of Engineering and Technology. We have been learning the subject basic electrical engineering, and we are in a continuation to learn about the AC circuits. Now, in our previous lecture, we have discussed about purely resistive circuit, purely inductive circuit, and purely capacitive circuit. Right now, in our today's session, we have to combine R, L, and C. So, in our first part of discussion, we are going to take a series combination of R and L, and then we apply the AC signal E is equal to V sin omega t. After that, we learn about the series combination of R and C, and subsequently learn about we combine R and C all together in a series. Right. So let's first start with the so dear students, we have been discussing about the AC circuits where in our previous session we have discussed series RL circuit. Now in our today's session, let us discuss about the series resistance capacitance circuit. This is defined as a series RC circuit. Now our terminology is same, where we have to first discuss about 3 points. So point number one, the relationship between voltage and current, the phase difference between voltage and current. Point number two, that is to draw the waveform and phasor diagram. Point number three is the power calculation. Right. So let us first start with the series combination of resistance and capacitor, where the voltage drop across the voltage where this is voltage drop across the resistance is VR, that is equal to I into R. The voltage drop across the capacitor, that is equal to VC, that is equal to I into XC. Right. So if for this series combination, now we apply the AC sinusoidal signal, Vt is equal to Vm sin omega t. Right. Now here further we discuss and taking the individual phasor diagram of resistance and capacitor, where for the resistance the phase difference is 0. So both the vectors starts at the angle 0. But this is not the case for capacitor. For a capacitor, the current is leading by angle 90, where you can see this diagram. Now my next job is to combine this two phasor diagram of R and C, and you will find the series combination of the phasor diagram of the series combination of R and C. That's what it is called. Phasor diagram is nothing but the master key for this. So now let's start and combine these two phasor diagrams of individual resistance and inductance. You can see on our x-axis the vector is current. Since voltage drop across resistance VR is in phase with the current, so you can see uh, VR vector same with the current vector, because both are in a same phase, right? But this is not case with the capacitor, where here the voltage drop across capacitor VC is leading by angle. Sorry, the voltage drop across the capacitor VC is lagging by angle 90 with respect to current. So you can see on a y-axis there is a vector of VC. Now since there are two vectors are moving in anti-clockwise direction, so your job is to find the resultant vector. That resultant vector we define as a Vs, and that is diagonally here. Right. So now from this triangle we can further going into detail. So before that we define here the difference between voltage and current. So here V is equal to Vm sin omega t, I is equal to Im sin omega t plus phi. That means here current is leading by angle phi with respect to voltage V. Right. So from this you can define here the value of current Im is equal to Vm by Z, where Z is defined as the impedance. So our next job is to draw the waveform with this respect, where you can define all the equations from the phasor diagram. So if we define here the waveform, where you can see the voltage V starts from the angle 0, but the current is already started with the angle plus phi. So here current is leading by angle phi with respect to voltage V. Right. Now next case we will define the power calculation. P is equal to V into I, where you can define here the instantaneous power is nothing but the multiplication of instantaneous voltage and current. So P is equal to V into I, where you define P is equal to Vm sin omega t into Im sin omega t plus phi, right? So once you define this particular equation, you are now multiplying by 2 and dividing by 2. In this equation, you can find Pt is equal to 2 Vmi by 2 into sine omega t into sine omega t plus phi. Now, by taking 2 as we are converting into c minus c by the trigonometry, you can see Pt is equal to Vmi by 2 into cos phi minus cos 2 omega t plus phi. Right? Since here first term we define Vmi by 2 into cos phi, it is a constant term. But the another term having cos 2 omega t plus phi, this is called fluctuating sum. So the average value of this fluctuating term is always equal to 0. Let's find the P average value by taking the total span of the time, which is from 0 to 2 pi. So P average is equal to Vm by taking the integration. P average is equal to integration from 0 to 2 pi Vm by 2 in bracket cos phi minus cos 2 omega t plus phi into d omega t. By taking the proper integration by mathematical terms, you are solving this equation, you will able to find the equation. You can see point by point. P average is equal to Vm by 4 pi in bracket cos 2 pi minus 0 minus Vm by 8 pi bracket sine 4 pi plus phi minus sin phi. Now further taking this term, and you can see here P average value is equal to Vm by 2 into cos phi minus 0. So instead of Vm and Im, I am going to take Vm by root 2 into Im by root 2. So the P average value is equal to Vm by root 2 into Im by root 2 into cos phi. Since Vm by root 2 and Im by root 2 is nothing but the RMS value. So you will find the P average value here. That is nothing but P average into I average into cos phi. So P average is nothing but VI cos phi. Right now we are further going into a detail of power calculation, where we need to find the power consumption by individual resistance, capacitor, and overall circuit power consumption. For that, we define here our phasor diagram. Now, from this phasor diagram, you can see you can extract a triangle like x-axis, y-axis, and the resultant value. So, from this, you can see that x is the cos component and y is the sine component. So from this you can be able to find total three individual triangle, which is defined as a vertex triangle, impedance triangle, and power triangle. So first we discuss about the vertex triangle, where x-axis is defined as a VR, that is equal to I into R. Same with the y-axis is defined as a VC, that is equal to I into XC, and the resultant vector V is defined as I into Z. From this you can see here total V is equal to under root VR square plus VC square. Since VR is equal to I into R and VC is equal to I into XC, so you will see here V is equal to I under root R square plus X square, where R square plus X square you can define as an impedance Z. So here V is equal to I into Z, or I is equal to V by Z. This is what the equation that you will get from this vertex triangle. Now since the current value is same throughout this series combination, so I remove the current from all the vectors, you can be able to find the impedance triangle, where you have a resistance, you have a capacitive reactance Xc, and the resultant vector as a impedance Z. So from this you can be able to write the equation of Z is equal to under root R square plus X square, and the resultant angle phi, that is equal to tan inverse Xc by R. Right now I am going to multiply this equation into all vector terms. From that I can be able to find the power triangle, and that power triangle you can see here from the x-axis is the real power, from the y-axis is a reactive power, and the diagonal part, the resultant vector always give you the power consumption from the circuit. So my first term is defined as the real power. This is because of the resistance. So that is equal to P is equal to VI cos phi, that is equal to I square into R. Same with the reactive power, that is because of the y-axis. So reactive power Q is equal to VI sin phi, that is equal to I square into Xc. And my operant power is the overall circuit power, that is S is equal to V into I, that is equal to I into Z. Right. So from these three triangles, you can be able to find the individual equation as well as the power equation. But what about the circuit efficiency? So you can see here from circuit efficiency, You can define in terms of the power factor, and that power factor is nothing but the cos phi. So from this power triangle, if you define your cos phi, but a power factor that is equal to ratio of real power to the apparent power, that is equal to R by Z, that is equal to cos phi from this triangle, right? Now, the value of power factor is always between 0 to 1, right? And then maximum it can go to 100%, right? So by this way, if you design a very good series RLC circuit or series RL, series RC circuit, the power factor must be between 0.7 to 1, right? So the range of this power factor is from 0 to 1, right? Now we further discuss about the individual powers from this power triangle. So my first term we define as a real power is nothing but the multiplication of RMS values of voltage and current with the cos phi. So here real power or active power P is equal to VI cos phi, that is equal to I square into R, and unit in a watt or kilowatt. Same way in a reactive power, because of the component capacitor. So reactive power is nothing but Q is equal to VI sin phi, right? And that is equal to I square into XC. That is in terms of VAR or kVAR, which is a voltage ampere reactive part. And the overall circuit power consumption you define as apparent power, that is equal to S, and that is equal to V into I. Since you put the equation of V is equal to I into Z, then Z is equal to I square into Z. That is in a unit of VA, voltage ampere, right? So by this way, you can find the individual power consumption from the resistance, capacitor, and overall circuit, right? Thank you, dear students. If you have any comment, please write in the comment box. Thank you very much.